Hello everyone, my name is Renuka, Assistant Professor in Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. So in previous class we have studied about parallel processing, parallel computation method, and what is the difference between microprocessors and microcontrollers. Single instructions and multiple data, and multiple instructions and single data, multiple instructions and multiple data. Correct? So today we are going to study about what is meant by digital signal processing. Okay. Before you could even start about digital signal processing, we have to know what is analog techniques that were actually used earlier, right? Earlier, like speech signals, and then you have a telecommunication and radar system were all actually used in analog interfacing and analog systems, okay, wherein you have signal characteristics being extracted through this analog mode. In analog techniques, especially the speech processing, telecommunication and radar systems, we used all analog techniques in order to extract the signal characteristics, right? So in digital, we have to have a digital data. Right. So before that we need to understand how actually we got all this information, how actually it got evolved from a simple analog processing to a digital. So there was a need in order to understand the analog signal characteristics of signal processing, okay, as well as the telecommunication and radar applications, because it will be accessed in a remote area, right. So now the need for digital technique and the constraints in the bandwidth of the signal that needs to be processed. So even if there was an analog signal could be a pressure, could be a temperature, they had a basic limitations, that is the bandwidth, because the signals will be in a varied analog format and that has its own limitations. So those analog signals had to be digitized. So that became a greatest challenge, right? So the special purpose ICs are required and high level languages as a compiler were to be incorporated. So why we are talking about digital signal processing is because there is a need to have a very good compilation techniques, okay, and accuracy of the detail, okay, so that there will not be any differences or a drift in any when compared to that of the analog signals, okay. So to have a sustained value throughout, so to have all these initial characteristics of a data, especially when you consider any analog signal like that of voltages, okay, or it could be a pressure or temperature, that needs to be correlated with digital data so that you get a better accuracy. That was a need, okay, to understand the characteristics of either the speech signal or it could be telecommunication or a radar systems, right. So now regarding the digital signal processing, first we need to know what is the process related interfacing. We already dealt what is interfacing. If you have a microprocessor, then you have an additional add-on ICs that will support a computer to have access to any other peripheral devices, right. So like that we have to have a process related interface, it process or it could be a plant, okay. So the instruments and actuators connect to the processor or a plant where most of these devices can be allocated to one of the four categories. So what you can see here, there are four major categories where earlier we have process related interfacing. What are the process related interfacing? First would be the digital quantities, then you have analog quantities, and third you have pulse and pulse rates and telemetry. So when we are talking about digital quantities in previous module, we have studied about the valve opening and closing, correct, switching on and off the switches, and then you have other digital, that is the digital voltmeters, which will have a BCD, that is the binary coded decimal format will be displayed. So all these are your digital quantities, okay. And then you have analog quantities where thermocouples. What are thermocouples? A temperature would be considered in terms of voltage levels, okay, or in strain gauge the pressure there would be considered as a which will be correlated with that of the voltage. So what will be the analog quantities? Analog quantities with respect to the pressure or the temperature all will be derived in terms of millivolts, okay. If I say 0.2 volts, 0.3 volts, so that will be the data, okay, of analog quantity, because it is continuous, okay, along the time. Then you have pulse and pulse rate. What is pulse and pulse rate? So switching between AC or DC motors, okay, AC or DC motors, that becomes a very important aspect, where each and every pulse, we have already dealt about what you mean by pulse width, right? The same way here you have a pulse and a pulse rate. Based on the timing cycle, you are going to access whether it is going to switch on or switch off. So you are sending a pulse on which the entire process will be dependent, okay. Then you have telemetry. Usually they'll be implemented in gas stations or even the electrical generator station. So telemetry is nothing but operating any equipment in a distant mode, okay, through voltage levels, okay. So those are your telemetry. So telemetry, usually they are employed in electricity substations or gas pressure reduction stations. So the best example, as we all know, about electricity substations, where you have a generator station, correct, where you generate the electricity. So you have mechanical energy being converted to electrical energy, and from there you have a distribution line, right. Distribution line could be 11 kVA or normal 230 volt like domestic, 230 volts and say about 15 amps or 440 volts, okay, for domestic purposes. So like that you have a distribution station, right. So those are nothing but the remote access. So you have a monitoring system at the station, okay, and it controls all other substations, okay. So this is about the remote access. That's the reason we say a process related interfacing. So there is a process or a plant, relatedly we have the interfacing required to monitor the plant or to operate. So the digital signal interface. So now when we are talking about digital signal interface, so there is a digital data, which means there should be a digital data, there has to be an interfacing unit, right. So let us understand that concept of digital signal interface. So now here if you see, okay, there is a block diagram. You have a CPU here, central processing unit, and you have a plant, correct. This is a plant, right. So you have multiple lines, right, from the input lines from the plant. So we shall assume that all the inputs from the plant are all your binary data. We'll assume, okay. If you're assuming all the input lines here are binary data or a digital data, let us quote an example like about one word, okay. One word let us consider as 8 bits, okay. So if I'm sending one word of data, we have 8 such lines which will be connected to the digital input register. Okay, if you see here, digital input register, as many number of the input lines you have, digital lines you have. So you have 0, 0, 0, 0, 1, okay. If you just 0, 0, 0, 0, 1, so you have 5, right. So 5 bits of data. If you consider that as a word, it is one word. So those many number of lines will be connected to the plant, okay. If it is 8 bits, okay, then you have 8 such lines being connected. So it is like having each line oriented for one single bit, okay. So that's the reason you have multiple lines here, and from a plant, okay, to your input registers are all binary. So let us assume that they are binary lines, and from this input register, digital input register, okay, it is connected to a address decoder, okay, through different bus. What are these bus structures? We know there are data bus, control bus, and you have a address bus, right. Now the plant output logic signal, let us assume as zeros and ones, and one word if I consider like about 8 bits. So we need to have 8 such input lines towards the digital signal or digital input register, okay. So now the inputs are either zeros and ones, so address decoder and select line. So here you have a decoder. So now if a plant is trying to send some input information here, that is zeros and ones, okay. So now it will be dumped in your register, right, zeros and ones. But logically here you don't have zeros and ones from a plant. It is again a voltage level. So 0 is considered for a 0 volt, and if I consider 5 volts as 1, okay, if I represent 0 volts in terms of voltage as 0 bit, that is a 0. Then you have 1 to be considered as a 5 volt. Okay. So then all these 0 to 5 volts will appear across this input of the registers, right. If there is any variation between 0 and 5 volts, if it is 2.5 volts, then you need to have a special kind of coders which can code these values, right. So now let us assume that is just zeros and ones here, that is 0 volt and 5 volt, so which will appear across the digital input register. So now it will not be sent directly to the central processing unit. So what will happen? The central processing unit will send a signal, okay, and there is an address decoded and it will be selected as per the individual lines. So there will be an address allocated for each and every line. Okay. So once this has been selected, then there is an enable signal which will be obtained from a control bus, that is from the program control. Okay. So this control bus will say that now I am ready. So it says it sends a ready signal. So once a ready signal is sent from this enable line, then you have these ones or zeros being sent through the data path. You can see this is the data path. So the data will flow from the digital input register, these data will flow accordingly, okay, through the data bus and it reaches your CPU. So this is your, the input interfacing between the plant and the central processing unit, okay. So we have two important signals here. One is the select signal will give you the address where exactly you have to place the data from the digital input register, and then enable signal will be sent by a control program through a control bus. Once the enable signal is activated or enabled, then what will happen? There will be a data which will be selected from the lines at the input, will be traveling through the data path, and then it reaches your CPU. Okay. This is how the plant works. But if you just look into this block diagram, we have what is called as status line is absent, right, which means that the status always represent what is the central processing unit, what is its what is its condition, is it ready, or is there any other interrupts that has been enabled, or there are any other action that needs to be performed. So we don't have a status signal. So there is a requirement of a status signal to know what is the processor doing, right. So now that's the reason sometimes if there are signals that will be sent from the central processing unit, that is your processor usually sends a timing signal. If there is any variation, if there is any mismatch in this input, okay, if there is any mismatch in this input while enabling the data to be sent, then the entire data will be corrupted and the other devices connected will be able to send any information to any other peripheral devices. So the important part of the entire process is the CPU, and its status has to be fed to your input register. So this is one of the drawbacks, but this is actually the basic building block of a simple digital input interface. Okay, how a plant, okay, will be interfacing the CPU through this digital input register. Okay. Now the very important aspect to know the read input timing signal. So when we are talking about timing, we know that a processor, we say that a processor is very good, it's very fast. What does it mean? It means that how quickly can you get the output for a given input. It should be less than 1 microsecond, but if it is more than 1 microsecond, it is still considered as delay, right. So now if we just look into the read input timing diagram, a CPU governs timing signal, as I've just told you. Transfers requires 3 cycles. What do you mean by that? If you see, this is called as a timing diagram. There are 3 major lines here. One is called as a system clock. Clock, as you know, it is on and off between pulses. So this is on time, this is your off time. You have a alternative on off signal. So this is your system clock. Okay. Now if I say that we require 3 clock pulses in order to get the address, what do you mean by that? I have to make sure within this time cycle, that is T1, T2, T3, I should be able to get the information or the data being transferred from the plant to the CPU or from CPU to plant, right. So, this is how it works. Okay. So, now for the first clock pulse, how does it function? So, the first initial clock pulse T1, you have a raising edge and you have a falling edge. The address lines, as I have told you earlier, if you just see here, we have address coder, right. So, we have address coder, there will be an address that needs to be assigned for one single line, right. So, now that signal has to be fetched and coded here well within this time schedule, that is before the switching on of the next clock pulse T2. So, within T1 you should be able to get the valid address. After that, at T2, that is the raising edge of T2 and the falling edge of T3, you should be able to receive all the data. The data has to be completely received. Okay. Then the falling edge of T3, what will happen? You should be able to send all the data, all the signal, the allocation of the address, the complete cycle of data has to be sent through the data path. Okay. That is from the data path to your CPU has to go between this T3, the falling edge of T3. So, this is the complete cycle for which the entire processor, the plant will send the data to your CPU, correct, through the register, that is in digital input register, right. So, now what is this T1 then? This is mainly if there is any mismatch in the timing signal, if there is a variation in the performance of a CPU, then this is like a additional add-on pulse wherein the raising edge of your T1 could be considered as you can still send the data even between T3 falling edge to T1 raising edge. So, this is how the read cycle is implemented. So, initially this is the allocation of your address, the read signal is initiated at T2. At the end of T3, the read signal should be completely sent. Once the read signal says, yes, I am ready to accept the data has to be transmitted well within T3 to T1. It should be completed well within T1, even if there is any variation in this, before T3. Okay. So, this is about the timing diagram and how the information is transferred from a plant through a digital input interface, the address lines. Okay. So, if you just see here, T1 negative edge is nothing but the variation in the component. So, as I have told you earlier, this is if there is any variation in the component, you can still send the data between T3 to T1. So, to send the simple data, how many cycles are we operating? We are using 1, 2 and 3, an additional half of the other cycle, right, other clock pulse. So, it is always required to reduce the number of cycles. Okay, you should reduce. If I am able to generate one or two clock pulses, and if I am able to achieve to send a data within that 2 clock pulses, which processor do you think will be more efficient? It is the second one, isn't it? Because the lesser the clock pulse, but you have a data which has been sent already, correct? What does it mean? It is nothing but the speedy operation, okay, or retrieval of data or sending a data or processing of data. So, it talks about the strength of your processor, okay. Next, coming to digital output interface. So, now after knowing the digital input interface, we need to know what is a digital output interface. So, you have a plant here, the block diagram, you have a plant, you have 3 lines, that is the data bus, control bus and the address bus. Then you have a address coder, decoder, and you have a outputs. These are your digital output registers. So, now the information from the CPU will be sent through the digital output register, and from the digital output register it would be sent to the plant. If it is a monitoring system, right, it says it sends a signal, like for example, valve open at this particular time because the temperature is very high or very low. Okay. So, these control signals will be sent. right? So what happens at this register is there should be a latch in the sense the register, there will be n number of data that will be sent, isn't it? Because they are all digital. So now you need to ensure that it has to be enabled only when there is a requirement. If there is an address for a specific line to be accessed, only then it has to enable. Otherwise, what will happen is there could be a variation at the output of the register. Okay, so a register required or a latch which can hold the data output from the computer. So there has to be a latch or a data output where you can actually have all the information be stored or the data output from the computer. To avoid the data in the register changing when the data on the data bus changes. So as and when there is a data variation happening at the digital output register, there is a variation happening at the register at the input of your plant, right? Input that will be sent to the plant. If there is any variation, there will be a mismatch, right? So that the latch of that particular output has to be controlled by this enable signal. Only when the program controller sends the enable signal okay, then only you have to have a data being transferred across. Okay, enable signal indicates device is stable and it can be ready. Okay, it can be ready to send the signal. So latch must be capable of accepting the data in a very short duration of time, because here the access again is the timing signal. So if the within a short duration of time you are able to send the data, a processor would have achieved a better performance. Okay. So if the logical level fails to operate actuators or plant, the higher voltage signals for low level signals are enabled. What do you mean by that? So now you are sending a signal, isn't it? You are sending a signal through the digital output register, right? So now if this digital output registers are zeros and ones now, okay, and you have a plant, and this plant will not accept like zeros and 1, but it will take in terms of voltages, 0 volts to 5 volts, let us assume. Okay. So if 0 volts and 5 volts are sent across to the plant, so if there are any actuators, okay, so if the voltage levels when it reaches to the plant, by the time it reaches to the plant is very low, what do? You have to make sure that you are sending a low level signal with a high voltage levels, so that you can enable the actuators to work. Okay. So that's the reason if logical level fails to operate the actuators of a plant, a higher voltage signal for a low level signals are enabled. Okay. Use of relay will provide electrical isolation between plant and the computer. So what happens? To accommodate this, we are using a relay. Relay will always have an isolation between the plant and the computer, so that it can transmit the information very efficiently. Okay. We have what is called as a pulse interface. As the name itself indicates, pulse and interfacing which is operated based on the timing signal, that is on and off, right, the pulse width. Fine. So this pulse interface is nothing but, if you just see here, this is the interfacing unit. Okay, it is same as before other input and output digital interfaces, except that the plant, okay, you have a plant here, you have the lines here, that is address, control and data lines. So this interfacing unit is nothing but the pulse. Okay, this pulse interfacing is incorporated using a pulse controller, or you can say pulse counters. Okay, so you are accommodating a pulse counter here. So what will it do? A counter is connected between the lines and the plant. The pulse output can, which means that the pulse output can take a varieties of forms. So here, if you just see, there are addresses, okay, and there are control lines and data lines. So now, if there is a variation in the pulse, okay, if I say that for 1 second you're going to send a data as positive, that is 5 volts throughout, and only at 0.1 second you drop the value to 0. Okay, so what happens? You have a long duration of positive pulse, right? So that is nothing but a series of pulse with a fixed duration. So you are fixing a duration for the operation. So this is nothing but you're controlling the action of the pulse based on your requirement. If you want the system to be on, okay, throughout, So what do? You just keep the high level, a long duration pulse, a short duration, or you can say a medium, or you can say customized pulse width modulation. We can study about it later, but you just need to know that the pulse output here can be varied. It also depends upon how a series of pulses are there. It could be fixed for one duration of time, or a single pulse with a varied length could be there, or for example, if you just go to the previous slide, here what do you say? You see there is a pulse, isn't it? If you just say this is a clock signal, what is it? It has a fixed duration of time. The duration between one clock to another is the same, right? It is not varied. So it comes under what? It comes under a fixed duration, a series of fixed duration pulse. Okay. Next, you have a single pulse of a varied length, that is T on and off could be varied. Then you have pulse width modulation based on the kind of requirement, okay, based on the kind of system that you are operating on. So these are the three different variations in your pulse interfacing, based on which you can actually control the operation of plant, monitor, okay, the plant through your control bus. So this is all about your in the study of different kinds of digital interfacing, the input interfacing, output interfacing, as well as your pulse interfacing mode. Thank you.